Hello everybody, my name is Harjinder Gill and we are Team Poggers. Today we're going to show network security attacks with my team members Sandeep Varma, Sai Krishna, Akhilesh Sharda. So each team member performed individual attack. So first attack was Mitnick Attack, second SYN-Flooding, third ARP Spoofing and MITM attack using Netcat, and fourth local DNS and cache poisoning. The Mitnick attack is a form of TCP session hijacking in which vulnerabilities in the TCP protocol and trust between two machines are exploited. The Mitnick attack establishes a TCP connection between victim client and victim server on their behalf and then naturally hijacks it. The attacker masquerades as a server and gets access to the client machine with RSH and implants a backdoor so that it can access the client anytime it wants by corrupting .ros file. There are three machines in the play. First, X terminal, second, trusted server, and third, the attacker. As we can see in the diagram, attacker wanted to access X terminal remotely and add a backdoor. The server can access X terminal without password due to trusted relationship between them, and attacker will exploit it. There are main four steps. First is information gathering. We need to use the initial sequence numbers to communicate with the terminal. Second, sequence flooding to mute the server. So trusted servers did not communicate with the X terminal. Third is spoofing the TCP connection. Fourth, running RSH and setting up backdoor. Nowadays, Mitnick attack is no longer practical because security in networking field is way improved than before. Back in the day, people used remote shell RSH instead of secure shell SSH like today. Now I'm gonna show my Python code and I'm gonna show the demo. So I have created three main files. First file is Mitnick acknowledgement file. This one I have created two different functions. First, it will send a spoof sequence to the X terminal, and then once X terminal has received the spoof sequence, then it sends back to the trusted server with a sequence and acknowledgement flags. To complete the three-way handshake protocol, then we send a spoofed acknowledgement packet. Once the flags are sequence and acknowledgement, it will send a spoofed acknowledgement packet. After sending the spoofed acknowledgement packet, three-way handshake protocol is completed. Then we can send RSS data packet, and XYZ will be created. So I will show you this, like how this is created. Then we will be using this second file to send sequence and acknowledgement packet. When the X terminal sends sequence, we have to send sequence and acknowledgement back, so it doesn't set a reset message and stop the connection. And third file is the backdoor file, in which after sending all the acknowledgement and completing the three-way protocol, we will be sending we will editing the ROS files and adding ++ on the ROS files to exploit the connection. Now let's start our Docker file. All the terminals have been started. Now we will run them. Now I will also run the trusted server. Now we are opening the rhost files. We are adding the rhost files, editing the rhost files, and adding our trusted server's address to it. Now we are changing the permissions of rhost files. Now we can see what rhost files contained. So it's 10.0.2.10. We will change this to ++. Now we can see the connection has been established. We can check the date without any ID and password. So the data has been displayed. So now we will do the sync flooding and mute the server. For just a safer side, I will close the connection between close the trusted server so it won't communicate with the X terminal. So we kill the X server. Now we will log in as the seed attacker, as we will be running our Python code from the seed attacker. We'll do the same here in another terminal. So we'll open the folder in which our Python files are present. Now we will start the Wireshark as well to capture the packets. We are running the first file that will send first sequence to the X terminal, and then if it's getting sequence and acknowledgement, then it will send acknowledgement, and after that it will send RSH data for XYZ file. So here we can see first sequence has been sent from our side to the X terminal, then we got the sequence and acknowledgement, then we sent the acknowledgement from our side, then session has been established and a remote shell command to execute. We can see this in our X terminal as well. Here, so we have created XYZ. So we'll close this now and we'll send sequence and acknowledgement to spoof the second connection. Here we have sent sequence and acknowledgement as well from 1990 server. So we can close this as well now. Now we will clear this. Now we can see like the handshake protocol has been completed. Now we will perform our backdoor. So now I will be running my Python attack file to create the backdoor. So we can see now it's writing the data. So now I think it has written the data, and we can check in our X terminal if we have if our host files has been changed. So yes, we can see plus plus has been added to our host files, so we have created a proper backdoor. And now the Mitnick attack has been completed. Thank you. Now my team member will perform his attack and explain further. Thank you.
Hello, this is Akhilesh, and I will be doing SYN-Flooding Attack in the four attacks that we're doing for the networking project. And basically, what SYN-Flooding does is it is a type of denial of service attack where the attacker repeatedly sends SYN requests, and these SYN requests are from random IPs and to different ports so that the victim cannot block one particular IP and falls under the attack. So what basically happens is whenever someone sends a SYN request to another system, if a server is sending a SYN request to the client, basically the client responds with a SYN plus acknowledgement packet, and waits for an acknowledgement packet from the server on their side to complete the connection, three-way connection between them. So while the SYN plus acknowledgement packet is sent by the client, it basically puts the request in the transmission control block. And basically what this queue has, this queue is full of half requests, half opened requests, and basically this is what the attacker uses in this case. And so normally every client that is sending a SYN, that is sent a SYN plus acknowledgement packet, responds with a acknowledgement packet of their own to the server to complete the handshake. But in our case, the attacker will never respond with this acknowledgement packet, and this is why there will be multiple requests in the transmission control block, and the queue will be full. And once the queue is full, basically the client stop accepting any requests at that point. So basically, a SYN flooding attack is just so many requests at a time that it just blocks the entire network of the server, and that's what we'll be doing over here. So now I'll move on to the demo. And so as you can see over here, we have three instances up. So the first one, which is 10.9.0.6, this will essentially be a user that I'll use to do telnet to my victim. And I'll just use this server to show that the network of my user is blocked. The 10.9.0.1.5, this IP will be used as an attacker, and this is what will send the command that will send unlimited SYN requests from different random IPs. And at last, 10.9.0.5 is finally our, it's going to be our victim in this case. So the first instance over here, this is the 10.9.0.1.5, which is the attacker. The middle VM over here is going to be our victim, and this is what I'm going to use to show basically that we are under attack. The victim is under attack, and how I'll show that is first I'll just telnet to that victim IP, and currently if everything works fine, this should just work. Okay, so as you can see, now we are telnet. Now the telnet connection between this user and our victim is made, and currently we are on the victim. We are connected to the victim right now. If I put this command, so basically this command will show us what all connections are coming through right now. So what all ports are open, what all ports are listening over here. And 23 is the telnet connection, so it's looking for all the telnet connections right now that made to the victim right now. And so what I'll do right now is now I go into my attacker, and what I'll do is I'll first of all I'll just show you what the what the what the function is that is going to do this. So basically what we've done here is we've created a very simple program that is going to do a SYN flood attack. So what Networks is essentially a tool that is used by network administrators as well as network hackers essentially. And what this does is this tool allows us to make a SYN flood request. And so basically we just use this tool. Now 76 number is essentially the tool number, and this is the one that is used for SYN flooding, so that's right. And minus I is the IP. This is the IP that we're going to do. This was the victim's IP. The port number is, I've taken it as 23 because I'm showing this example via telnet, and 23 is the port for telnet. So basically I'm going to be blocking all the network on this port, this IP. And minus S raw, what this does is essentially this is telling networks that I want all the IPs to go at random. All the IPs that are making the attack are going to be random at this point. And OS system basically is just running this command in the background. So just as you saw, now I'm going to go back into my attacker system, and over here I'm going to run that command. Volumes. And now the I've run this file and the file is running in the background. It runs infinitely because they're sending infinite requests. And just to prove how it's working, earlier you saw there were only three connections right now to our in our victim, right? And now if I do the same command, which is going to be netstat TNA, this is going to now, as you can see, there are so many send requests being made, and none of them is established. Earlier it was listening at two, and then there was one established connection. All of these SYN requests are open right now. And this is what basically SYN flooding is. And as you can see, all the IPs are random, and that was because of minus S raw option that we sent in our networks command. And if I now, how I'll show the network is blocked is if I exit out of the telnet connection that I made from the host, right? Now I'm back to the original user. And what I'm going to do is now I'm going to try to make this connection all over again, the one that we made before. So after the attacker has made that request, we're trying to make a telnet connection all over again. Now, since the transmission control block queue is all full, it's taking so much time before the telnet goes through. And usually, since the network is blocked, the telnet connection will not go through. It'll say that the connection timed out, and that this is where it shows that the attack was successful. And as you can see over here, now it says telnet wasn't able to connect and the connection timed out. So here we go. This was SYN-Flooding Attack, and as you can see, it was successful. Thank you so much.
Hello everyone, I'm Sandeep Varma and I'd be discussing and showcasing ARP spoofing and man-in-the-middle attack using Netcat. I've chosen this attack because ARP MITM with Telnet and ICMP redirect MITM with Netcat was discussed in class, but not ARP MITM with Netcat. This was not part of any lab assignment as well, so I have upgraded and modified the existing code to change the alphanumeric messages to X's, and simultaneously I'm getting the MAC address of the victim based on the IP within the code. I have made the entire code dynamic to enter any victim machines during runtime and change any kind of alphanumeric messages instead of just static ones like seed labs, which was discussed in ICMP redirect MITM lab. I will initially explain the process in ARP MITM attack based on the image displayed. Firstly, the attacker spoofs the MAC addresses of the victim, then he hijacks the sessions and then listens the communication between them and finally intercepts the messages. I will explain the difference between ARP MITM and ICMP MITM here. Firstly, ARP is a protocol used in a LAN to resolve the MAC address of next or final destination IP. Therefore, an ARP MITM attack works by spoofing a MAC address within a LAN in response to a victim's ARP request. If the MAC of the intended machine is successfully spoofed with the attacker's machine, then the victim will send traffic to the spoofed MAC addresses instead of the destination MAC addresses. It follows that for this attack to be successful, it must be executed within the victim's LAN. Additionally, for an ARP spoof to be effective, you have to be able to respond faster than the actual destination ARP response. Whereas an ICMP MITM attack, on the other hand, is accomplished by spoofing an ICMP redirect message to any router that is in the path between the victim, client, and server. An ICMP redirect message is typically used to notify routers of a better route. However, it can be abused to effectively route the victim's traffic through an attacker controlled router. While this attack does not require LAN access, the disadvantage is that many routers have static routers or do not accept process ICMP redirect packets. So simply speaking, the ARP protocol uses the MAC addresses while the ICMP redirect uses the routers. So uh, now I'll explain the codes which I have modified within the existing program. So here masking the victim sender is all alphanumeric data. I have written a function which takes the data from the sender and that comes to the attacker. The attacker decodes the message and then whatever are there, the alphanumerics like 0 to 9, A to Z, either capital or smalls are changed to X using pattern matching. And then the new data is encoded and it is sent back to the receiver victim B. And the dynamic entry of IP addresses and fetching the MAC addresses is also done within the code for both spoofing as well as MITM Netcat. Here, the attacker can dynamically enter the IP address of the host A machine as well as the host B machine and the MAC of both the machines would be fetched with this function get MAC address, which is a default function, which is one of the package which I downloaded, and dynamically this would be fetched. And here iFace is also entered by the attacker. It can be either ETH0 for Ethernet or VLAN0 for VLAN. Here in this case we are using ETH0, the Ethernet. Now I'd be moving forward to the code. Now I'd be demonstrating the attack using the ARP spoofing and the man in the middle using Netcat. So initially I am within the folder structure of ARP final, which is my folder which has both volumes and the Docker file. I'd be launching the terminal. I'd be giving the sudo access, and then I'd be going to my folder over here. I'd activate the Docker and all the files within this are activated. So right now M is the attacker machine 105, the IP which I'd be using as an attacker. Host A and host B, or victim A and victim B, are 10.9.0.5 and 10.9.0.6, which are the victim machines which I'd be using. So once these are up, I'd be going to a different terminal, and then I'd be activating and launching all the three machines, the attacker, the victim A and victim B. So as discussed, I'll first launch the attacker machine. So this is up. Now I'd launch the victim A machine, that is potentially a sender as well. So this is also up, the host A machine. Now I'll launch the host B machine, that is the victim, that is B, that is the receiver who would be receiving messages from A. So all the three machines are active right now. I'd also open the attacker machine once again, because I'd be running the Netcat program right from here, the attack program. Now I'd establish the communication between A and B and show you how exactly they communicate. So I've activated on host A, now I'm activating on host B. So I'd send hello from host A to host B, and this has been received right over here in the host B. Vice versa, I can do the same. Hi A, how are you from B? And this is received over here. So now I'd be showing you their MAC addresses as well. So the MAC address of B is 06. And the MAC address of A is 05. We're just considering the last two digits over here. So right now from the attacker's machine, I'd be running the program ARP poison MITM.py. So this would be spoofing the MAC addresses of victim A and B into the MAC address of the attacker. This way the attacker can see the communication between both the victims A and B, whatever messages are being communicated between them. So I ran the program and it is prompting me to enter the IP address of the host machine A. This is completely dynamic, nothing is within the code. Now it's prompting me for the receiver's machine. And now the packets are being spoofed. So I just show you the MAC address over here. As you can see, the packets are spoofed and the MAC address is also spoofed. As you can see, it has been changed to 69. Before it was 6 for the host B. and the same would be happening for host A. See, as you can see here, this was 5 initially, and now it's been changed to 69. So I just show you the program as well. Uh, so I'm just taking the input over here, nothing is static over here, and the MAC address is fetched dynamically once the IP is entered by the user, the attacker in the runtime. And the IP forwarding is also done here within the program, and the attacker needn't to do anything statically or explicitly in the command prompt before running this program. This is automatically turned off with 0, and the IP forwarding is turned off, so 0. So right now this is running, and this has been up, everything is running well. So now I'd be running the program where the communication would be happening. I'd just turn up the communication over here for both the channels. So now both of them are live. Now I'd run the program over here. So it's prompting me to enter the host A's IP address. As you can see, it has dynamically fetched the MAC address of host A. This is 5. This is within the attacker's window, and now it is prompting me to enter the victim B's IP address. So I have entered that, and it has dynamically fetched the MAC address as well over here. And the interface which we are using here is Ethernet. So as we are on the same network, so I'll run it. So the attack is live as of now. And I'd send any message right from here. So I'd say, "Hi B, how are you?" The program is running. We'll just give it a moment because it's being spoofed. Yeah, so see, as you can see, the entire message got spoofed. "Hi B, how are you?" So here, "Hi B, how are you?" But here from B to A, the communication is perfectly all right. So B will send the message, "Hi, I didn't get any message from you. It is all X." It is all X. So the message has been received to A properly, but the victim A would say that it has been sending it properly. While coming here, see, everything is masked over here with X's. And the attacker machine can read each and every line of that. It has the entire data of sender A. So this was sent by the sender A, but it wasn't received by B, but it was received by the uh, attacker. So he's the man in the middle over here. So this way it's running perfectly all right, and it works for all the alphanumeric data like attack 90. I'd just say, and see, everything is masked. I'd say different edge case. I'd give a space. This is done. I'd give a mix of characters. And see, this is work. And the reverse channel would be completely working fine, like B to A. So this is the attack which I have implemented. I just show you the code as well. So here everything is dynamic. The attack starts from here. It takes the IP address of the host A and host B, and it dynamically fetches the MAC addresses in the attacker machine, and also the interfaces dynamically taken. Once it goes into the program, here the data is getting fetched by the attacker right from the host A machine. Then the data goes to the replace sequence function, where any alphanumeric data within the pattern is getting changed, and the data is decoded and coded and is sent back to the program, and then it is sent further to host B. So this is about my program, and now I'd explain the novelty of this attack. So the novelty of this attack is that it can mask any alphanumeric characters dynamically during the live communication between two devices. The attacker can see all the messages from victim A and send masked messages to victim B, who is the receiver. The MAC addresses are also fetched dynamically during runtime after the dynamically entered IP addresses by the attacker within the network. Here, nothing is static, as you have seen both the programs. It can be the attacker to ask for money to victim B in order to unmask the messages, as the attacker has all the messages from victim A or the sender. He can use this in order to fetch money. This could show that there is a security flaw within the network. Further, he can also tell the MAC address and IP address of both the victims, which would disturb and fear the victims on the same network. So this could cause a lot of problems to all the victims over the network. And moreover, during spoofing, the IP forwarding is set to 0 within the program, and the attacker does not need to do it explicitly while launching the attack. Thank you very much. This is all about my attack, ARP spoofing and uh, man in the middle attack using Netcat in ARP. Thank you.
Hello everyone. The attack on which I worked on is the local DNS and cache poisoning attack. Before talking about the attack, let's talk about what DNS is. If we want to send a message or a request to a destination, for example, google.com, we usually we don't remember the IP address of google.com. We just remember the name, but we need an IP address in order to connect with google.com. So this is where the job of DNS comes in. So basically, what DNS does is it translates the IP address of the google.com into the name and vice versa. It acts like a phone book. If we give a name to it, it'll give us the IP address, and if we provide the IP address, it gives us the name. This is how the DNS works. Let's have a look at the lab environment. Let's look at the basic setup of the environment. So here we have the internet, then the router, and we have an attacker, a user, local DNS server, and an attacker's name server in a single LAN internet connection. Let's have an overview of how the process works. So in the beginning, for example, if a user wants to send a request to www.google.com, so this is the user, this is the local DNS server, and this is the global internet. So for the first user, before sending a packet as a request, it checks in its own /etc dot slash host file. It's a static file where most of the mapping is done. If the mapping is not found in this file, it starts looking for it in the local DNS server. So basically, local DNS servers has a cache that stores cache memory for a certain amount of time. So it searches for the mapping inside that, and if it is not found even in the local DNS server, the packet is sent to the global internet from the root, then to .com, .ca, .org, and then eventually to www.google.com. So there will be a number of packets that will be sent from user till the internet, and every packet sent creates a point for the attacker to launch his or her attack. So in the first case, that is DNS local attack, a attacker. So this is the first attacker in the first case, and he picks in the packet that is being sent from the user to the local DNS server, the request packet, and he spoofs it and eventually sent it directly to the user machine as a response. And in the second case, the attacker, this time he is present between the local DNS at the local DNS server. So he grabs a packet from the local DNS server that is being sent to the internet and spoofs it and sends it to the local DNS server, where the local DNS server stores it as a cache. Have a look at the implementation part. So we have Docker that is up and running, and we have 4 different containers: the user, the local DNS server, the attacker, and the router. So let's first have a look at the cache of the local DNS server. So this is the cache. So we have flushed away the previous cache we had. Uh, so now the cache in the local DNS server is completely empty. So let's go to the user and use the dig method. Use the dig command. It's nothing but DNS information grouper. So let's start with dig www.uwindsor.ca. So we can see that we get the information of the DNS and we have the header part, question section, and the answer section. And the answer section has the original IP address of uwindsor.ca, www.uwindsor.ca. Now let's have a look at the cache that's being generated. So there's a lot of information that was generated in the cache. Let's filter it out using the grep command. We can see that the IP address of uwindsor.ca was stored in the cache memory of the local DNS server. Let's clear it out again. Yeah, it's the IP address or any information is no more available in the local DNS server cache. Let's start the attack. So the attacker is running his program and it's running fine. And let's now take the same host name with from the user. We see that the IP address was spoofed. It's now 13.14.15.16. So this is how an attacker present in between the local DNS server and the user spoofs the IP address of the request that was sent from the user and creates his own IP creates his own spoof packet and sends back the malicious IP address to the user. Let's have a look at the program. So we can see that here. So basically, a DNS structure of a DNS packet has three different parts: the IP header, the UDP header, as well as the DNS header. We can see that the same thing in the attacker section. So these are there's the IP header and its components, the UDP header, the port number, and everything is present in the UDP header as well as the DNS header, where all the flags, the request query flags, the opcode, and the R data, the QD packet, everything is present in the DNS server. So in this case, we have an attacker code where we filter out the packets from the source host to the internet. There's the source host. So we are filtering out and sniffing the packets that are sent from the source host and changing the IP header, making a spoof IP response packet where we're changing the destination as well as the source. Similarly, for the UDP header as well, we're changing the port and the port of the destination as well as the source. And we are setting up the answer section. And our data is the spoof IP address that we are sending, the 13.14.15.60. And we are constructing a packet and then sending it. So this is how the user attacks the local DNS server. But if you see that in the cache memory, we still say the original IP address of www.uwindsor.ca. So the effect in this is very minimal, as if the user sends the request for the second time or the next time, he'll again get the original IP address instead of the spoofed address. So in this case, the attacker has to continuously keep sniffing and spoofing the packets in order to retain the effect. But instead, there's another process called the DNS cache poisoning, where we poison the complete cache that is present in the local DNS server so that the effect lasts longer. Yeah, to maintain the effect, to maintain the effect of the attacker lasts longer, we have the second implementation called the DNS cache poisoning attack. So let's look at the implementation of it. So let's clear up the cache first. Let's flush it. We see that the cache is completely empty now. So let's we have stopped the previous task, and now let's go with the task 2. Now the task is running. Let's try digging it again. Yes. Now we see that it is spoofed again with 13.14.15.16. And now if we have a look at the cache that's available in the local DNS server, see the cache is generated. Let's filter it out. Yes. Now we see that the www.unc.ca has an IP address of 13.14.15.16 stored in the cache, and this is how we poison the cache memory of local DNS server. So let's stop the program, and so the program is structured in a way that the cache lasts. So we have this numbers 259200. These are the seconds. In the sense, these are the cache lasts up to 3 days longer, and this effect of spoofing lasts up to 3 days. So let's we have stopped the program, right? Let's try digging it again. So whenever you dig the send a request to www.unc.ca, we get the spoofed IP address of 13.14.15.16 until unless the same information lies in the cache memory of the local DNS server. Even if the program's running, the attacker doesn't have to keep on attacking on every single request. So here we are filtering out the packets that are being sent from the local DNS server. So we have the local DNS server address as 10.9.0.53. The same way, so we are filtering out those packets, and we are creating the IP header. Since the response packet has a different destination and source, we just swap the destination and source of the IP header. The same way the ports of UDP header and the answer section. If you see, this is TTL is called time to live, and this is the time until which the cache in our local DNS server retains. And this is the spoof IP address that we have maintained, and this is the DNS packet, and there's the so these are all the information. So we are trying to spoof the exact replicate exact same packet that is being sent. So we take all the flag information of all these flags directly from the packet that was being sent. And we are creating a spoof packet using all these IP header, UDP header, and as well as DNS header, and sending it. So this is how we spoof the IP. This is how we how the DNS local as well as the cache poisoning attack works. Thank you.